Ladies and gentlemen, today I will speak about introduction to limits, which is a basic concept of calculus. In my speech, I will be speaking about mathematics as an experimental discipline, which means that using concrete examples, I will go to theoretical conclusions. In this moment, I will see limit as an infinite progression. And I will try to demonstrate that such progressions can converge, and in more detail example, I will show that a function which is not defined in a limit, in a point, can have its limit in the point. So the value which can be proclaimed as would be the value in the given point. And later in my next lectures, I will be speaking about converging, diverging behavior near this point. Converging, this is our today's example. It means that we will converge, we will come to the point, but diverging means that uh, the approach can never reach, I would say, an agreement about the value. And then we do some conclusions of it, which are more. Uh, why we can understand mathematics as an experimental discipline? Mathematics was always, during the history, done by doing, and new knowledge come from those facts, which means that from concrete knowledge about calculations, measurements, star positions, and so on, we could learn what is necessary about, and we have to generalize this knowledge. In this case, in modern and contemporary ways, we use specific hardware or specific software, which means that we have to change our teaching strategy, and I will show you such an example. So we will have no prescriptions how to follow, just we try to be creative, think about what we are doing. And naturally, we will try to get a benefit from this solution. What does it mean considering limits? In calculus, it means to manipulate with very large and or very small numbers, which means numbers which we can never reach properly, but we still can work with them mentally. Without computers, such calculations would be very, very difficult because they often use multiplications and in fact, any mathematical function. So we have to distinct between these calculations we will provide in Excel, and technology will be only a carrier of our manipulation. Look, let us have a function which is not defined in a point x equals 2. This is an example of such a function. X squared minus 4 divided through x minus 2. Naturally, in the divisor, if x is equal to, there would be division by 0, which is naturally impossible. If we put this to Excel, and we take place interval near the point 2, in the given case, x is from changing the values from 1 to 3, we see that when x is equal to, naturally we divide by 0, which makes a fail, and when we draw a graph of this function, suddenly there is strange gap, why unusual behavior, and so different spreadsheet programs can differently react to that. So the graph is typical for Excel, but can be different in other spreadsheet calculators. What to do? So we say, okay, this is undefined. So we simply we delete this cell. And now we have a sequence which is in the graph represented by a gap. Okay, fine. Up to now, everything's normal. Nothing special happens. But we can ask, what happened if we would go closer? Because we go by 1/10 from 1 to 3. What if we would go in a smaller interval with smaller steps? Here, on the next slide, we go on the interval which is closer, and we make steps from left and from right. We try to reduce this empty interval, which is here 1/10. So the next slide shows what happens. Now the interval is from 1.9 to 2.10, which is 10 times shorter. And we see that the behavior of the function is the same. Again, it is undefined in point x equals 2, and there is no value in 4, sorry. Now we reduce the interval again, and we see the same behavior. If we compare these three pictures, the three graphs, we will see this. Yeah? Do they look similar? Yes, they do. In fact, each of those, the first one is the leftmost one, highest one, is the original, and then it's narrower and narrower. And we could go to the infinity. That's why I was talking about infinitely small and infinitely big numbers. We can shorten the interval, and the behavior of the function will still remain the same. What we can tell, if we go to 2 from the left, it means that values of fx grow up to 4. They never reach 4. When we go from the right to 2, the values of fx decline, but still are all greater than 4. So, there is another observation. The closer we are to x equals 2, the less is difference from 4. So, the conclusion is, if we could reach, we cannot, 2, the value of fx would be 4. Which means reaching x equals 2 is a dream. We cannot do it. But what we can introduce is the concept of limit, which says if we would reach 2, the value would be 4. Yeah? And the notation is like lim for x equals to 2 of the function is 4. And I showed here what those values 2 and 4 in our meaning. Okay, and that's in principle everything in this very simple case. There are more complex cases, but I will show about them in the future. Thank you for your attention. And if you have any questions or comments, don't hesitate me to write to my below email address. Thank you.